And what we see for AGC, 20 times AGC, we take the minimum. And when we take 45 minus minimum, we show the maximum AGC. So you see in this, in two items that I mentioned, energy and AGC. Also on this top is the average of all 3,000 AGCs that we measured minus what it should have been. So in this information from our San Jose office headquarters, we see minus 1.7 dB less than up to that perfect. The number one next to it is the RMS of all these 20 times 3,000 AGC readings. This is another very important characteristic. When we see variations in the AGC, it means presence of some interference. Next item is the volume under the area, under this energy, which should be constant because AGC is keeping it constant. 20 means we took this sample 20 times. Okay, now these four items, none of them by themselves can say anything concrete. We should look at four. We should look at AGC plot. We should look at the shape of the spectrum, and we should look at the average, this how much is below what the perfect number should have been, and the RMS. So these four items are the thing that we measure after the RF processing. This is the actual picture of our spectrum that we measured in our San Jose office. It's kind of calm. This is GPS L2. Here is our fault. Here, 51st harmonic of a clock inside our receiver. If you have a radio station near you, you can plug it in, and in each band will show the harmonic that may that fall within your spectrum. Anyway, we have corrected all these. I just want to show how detailed this spectrum looks into the band, and it looks where it should. No spectrum analyzer, 30,000 or 100,000 can show such detail. This is, again, 40th harmonic of our 30.775 megahertz frequency of our display, which we corrected. So the other things are just some things are on the air. And if you see very sharp lines, is because this is the maximum of 10 megahertz. You can spread it a little bit in your mind that these are 10 pixels shrunk together and take the maximum. So GPS L2 in our San Jose office is not affected. GPS L5, there is something in the background, but still we don't see anything important. San Jose, test 1 on GLONASS L1, it's clean. GLONASS L2, we see something in the background. This is 20 samples. Every line is 20 seconds, the total of 1 minute. There is something in the air. Is it the handshaking between CDMA or something? We don't know. This is an unauthorized signal within the GNSS band, within GLONASS L2 band, but it doesn't have much effect. I just want to say that we see such things to this detail for the first time. Now, this is not the whole picture. We will go now after signal is processed digitally, and we say, what did we expect if the system was best, and there was nothing in the horizon. This is our signal color-coded signal of satellites as we expect according to their elevation angle. Blue means the satellite signal to noise matches almost perfect expectations according to the both theoretical designs and things that we had seen around the world. Green means 3 dB less. And red means at least 6 dB less. So this is the picture that we see in our San Jose office. This information is after the signal is processed digitally. And this is a polar plot of the same color-coded information to know maybe the satellites are blocked by buildings or something that don't think if a satellite has low signal to noise, know where it is to be able to decide why it has bad performance. Now, this is the summary of all that you saw in these previous slides. This is the deviation from maximum AGC that was supposed to have. GPS L1 is minus 1.7, minus 1.1. These are all okay. We give a passing grade. But we don't like these fluctuations. It was okay. And as you saw, there was some on the AGC fluctuation. It showed it had a pattern. We don't know what it is, but we don't need to go back to those slides. These RMS numbers, it will show us that there was something in the air. And of course, by looking at the shape of the spectrum and look at the energy, we can see where those interferences are. This is the summary of numbers after digital processing. GPS L1 was 3.8 dB lower than what it should be. GPS P1, 5.7 dB less, and there were 10 satellites for CA and 10 satellites for P. Similarly, for GPS L2, because we had only 2 of them had CA code, and all 10 had P code. These are the numbers. GLONASS, minus 2, minus 0.2, minus 0.8, and GLONASS L2 the same. So GLONASS L2 had a little interference in our area. So all these together, you cannot look at one item and make any judgment, because you may have RF has interference, but because we have 10 dB of headroom, you may see perfect picture in here. You have lost only your headroom in the RF section, means interference was not big enough to kill the receiver, but it reduced its head margin. So not looking at one number cannot make a conclusive judgment. All numbers together, if they are clean, then we give it a clean bill of health.